So, welcome to the CFD class. So, in case of CFD, in the earlier presentation, I have shown how we can classify different partial differential equations into hyperbolic, parabolic, and elliptic equations. Now, in CFD, our main aim is to discretize this partial differential equation. So by discretization, it means, suppose this is a line and I know the value at this point, I know the value at this point. So I do not know what is the value at this point. So by value I mean it may be heat, energy, let us say heat energy. So some heat has been applied to this part, some heat has been applied to this part, and I know what are the heats are. So what will the heat at this part? So when we know this answer, what we do is we generally discretize the partial differential equation which represent the transfer of heat from this point or this point to this central point. So this is what we do in case of this type of questions. But by discretization, that what we mean is to differentiate an equation, a partial differential equation, into each point where its solution is stored or its solution is available. So that is what is discretization is. Here we do a prediction of a point which we do not know, which we have no information. So we use those algorithms to retrieve the information from that points. Suppose this is the image of a certain wavelength. Now, for some reason, our satellite has failed to capture this part of the image. But this part is clearly visible, and this part is also clearly visible. But I do not know what is it in this part. So that is why, with the help of information from x1 and x2, they try to predict the same information available at this location for y1. And this is generally done by the governing equation of the processes. Like if you want to know the amount of heat here, with the help of the heat here and here, then you are using the process of thermodynamics to know what is the temperature, what is the heat available in this part, right? So and this process of discretizing an area into different parts, or precisely different equal parts, this type of process is known as discretization, right? Now, you see, in this brief presentation, I will discuss about the Taylor series expansion method. What is forward difference, what is backward difference, and what is central difference. The basic aim of this process is to know the value of y, or the equation, objective equation, for a value of x, right? So generally, partial differential equation can be is differentiated with the help of discretization, and this discretization is done by the forward difference or backward difference or central difference expression that is being found out with the help of Taylor series expansion method. So we want to expand this function fx, right? around a point A. And let us say if x is equal to a plus h, where h is actually the variable and a is an arbitrary constant. H is the variable and a is the arbitrary constant. Then we can expand the function x into this. Okay, and if x square is that function, then and x is equal to 3, we can say f of x is 9, and f prime x, that means derivative of f x is 6, because the differentiation of x square is 2x. So note down these 2 points, then it will be useful later on. When a is equal to 0, right, then this series is termed as Maclaurin series. This is the, what I say, Taylor series expansion of the function x at or around or about the point C, about the point C, right? So this is your Maclaurin series. Now you see, let us say that in the earlier series we have said that x is actually the h plus a. So h will x minus a. And then this thing can be put into this here, f of x, right? And then the earlier series will change into this form. Okay, and this is also known as Taylor series of ascending power of x minus a, right? So this is your Taylor series expansion. Now let us say that what is the Taylor series expansion of function x at xi. So you put the value of xi as x in this function and you will find a series. And then if I say what is the value of function x at xi plus 1, and then I told you to reconstitute this series again, then you will have two series. One will have f of x I, another will have f of x I plus 1. And now if I deduct f of xi from f of xi plus 1, then what we'll find is, we'll find that f prime x into del x. So what will happen is f prime x will be equals to f of xi plus 1 minus f of xi divided by del x. This is also known as the approximation of the derivative of function x with the help of forward difference. Okay. So when I deduct this, it is given like this. And if I want to find the derivative, approximate the derivative of function x with the help of backward difference, what we do is we deduct function of x at x minus 1 from function of x at xi, and we get a value like this of f prime x. Now, if you add the value of f prime x at xi with the help approximated with the help of forward difference, and the value of f prime x at xi with the help of backward difference, you will find that this term will remain. F of x at I plus 1 minus f of x at I minus 1 divided by 2x. So this is your approximation of derivative of the function x with the help of central difference. So let us take an example. F of x is actually x squared by 2x. Its step size is del x equals to 1. So what I am saying is find the derivative approximation of fx with the help of forward difference, with the help of backward difference, and with the help of central difference. So here the point of interest is xi at 3. Step size is assumed to be 1. So what will be your xi plus 1? We know that xi is 3. So xi plus 1 will be 4. Why? Suppose this is the domain, and this is the point 3, x is equal to 3. And let I indicate this point as I. And then this I plus 1 will be 4, and I minus 1 will be 2. So that is why this xi plus 1 is indicated as 4 if xi is equal to 3 and xi minus 1 is equal to 2. So accordingly, what we have done is we have find out the value of the function at the x is equal to I, which is 3 in this case. So it will come this 3 9s plus 6 15. And then we have found out the value of xi plus 1, that is 4, right? 4 squared is 16 plus 8 is 24. And value of xi minus 1, that is 2. So 2 squared is 4 plus 2 into 2 4, 4 plus 4 8. Okay. So now let us see the approximation of f prime x with the help of f xi forward difference. So f of xi plus 1 is what? This f of xi plus 1 is your 24. In the last slide we have found it out. And f of xi, that means basically xi is 3, xi plus 1 is 4, and this function of xi is actually this function x, which is x squared plus 2x. So at xi plus 1, I can write 24. At f of xi, that is f of 3, that is 9 plus 8, sorry, 9 plus 6, this is 15. So 24 minus 15. Step size is 1. So 24 minus 15 is 9. This is what they have said. Then here what we have, this is our 15. This is our 8. So 15 minus 8 by 1 is 7. This is approximation of a prime x with the help of backward difference. And then central difference, the approximation of a prime x with the help of central difference. The xi plus 1 is 24, a of xi minus 1 is 8. So 24 minus 8 divided by this is 2 into del x, the step size, that means 2. So this is basically is 8. Okay. So that was the differentiation or finding of double derivative. In the previous slide, what I have discussed is the differentiation of a function x with the help of forward difference, backward difference, and central difference. Okay. Now I will see the derivative or derivation of function x by the conventional method, not the discretization method. So as f of x is x squared by 2x, so a prime x will be your 2x by 2. Now x is 3, so 2 into 3 6 plus 2 will be 8. Now you can see from the earlier slide the differentiation of or derivative of fx with the help of forward difference. That means a prime x with the help of forward difference is 7. With the help of backward difference is 9. With the help of central difference is 8. And by the conventional method also, the differentiation of function of x is 8. So this method and the conventional method is equal to each other, or we can say it is the most accurate compared to the differentiation method, conventional differentiation method. So the central difference is more accurate if we compare the result of derivative of function x by the conventional method, right? So this is overall what is Taylor series expansion is, which is very important. You must remember how we have differentiated function x with the help of forward difference, backward difference, and central difference. So basically, in case of forward difference, this f of x at or around a point A, or I can say around a point I, you have to find the Taylor series expansion of function x around the point I. Then the Taylor series expansion function x around the point I plus 1. And then you have to find the Taylor series expansion of function x around the point xi minus 1. And if you know these three expansions, you can find the value of f prime x with the help of forward difference, backward difference, and central difference. How? So the value of a prime x with the help of forward difference will be the Taylor series expansion of this. The Taylor series expansion of f of xi plus 1, this is forward difference, minus the Taylor series expansion of function x at point xi or at point I. This is the Taylor series expansion of function x at point I plus 1, and this is Taylor series expansion of function x at point I divided it by x. Then you will find the derivation of function x. And by the forward difference method. And by the backward difference method, what happens is the Taylor series expansion of function x at point I minus the Taylor series expansion of function x at I minus 1 divided by 10x. This is the step size. And this is your derivation of function x with the help of backward difference. Now let us see for central difference. This is nothing but Taylor series expansion of function x at point I plus 1 minus Taylor series expansion of function x at point I minus 1 divided by 2 del x. So this will give you the differentiation of function x with the help of central difference. So this is the way you expand a function with the help of Taylor series expansion and find the derivation of that same function around some point I, or for derivation of the function with the help of the Taylor series expansion of the function around a point I. So this I conclude.